this is very preliminary work I'm doing with Rodriguez Mora, who is visiting Minneapolis. The motivations are things like this: relation between inequality and mobility, as summarized by the great Gatsby curve, which is the empirical finding that if you put inequality on the x-axis and the immobility on the y-axis, you get a positive relation. So countries that are more unequal tend also to be more immobile. So this may be due to institutional reasons. It may be due to characteristic of the genetic pool of the country. So we would like to investigate this. Second type of questions is the size of this intergenerational persistence. As in Clark's recent book, I want to contrast. Savi has a study that is also based on surnames and on the Catalonia census. And they do a calibration exercise fitting at the same time the informational content of surnames, which is the difference in R squared that you get between. So you get data on in their case education, then the surname of the person, and you can make an R square. You can make a regression of the education on the name, and then you make the same regression on a random reassignment of the surname, and you see the difference in R square. And the difference is large, and that is the informational content of the surname. Is how much the surname can explain of the observed asymmetry in the distribution of education. Then they reduce the estimation of the distribution of surnames to two parameters, the Gini and the number of persons per surname, and you get the calibration of the rho, which is the intergenerational persistence of education, which is 0.6, which is roughly ballpark of the 0.4 that economists find for income. So it's much smaller than what Clark find on surnames. Second thing they found is that assortative mating is large and has been increasing in the 20th century. So I would like to have some quantitative framework to study these. So the basic starting point is the Becker-Thomas model. You don't need to look at this because it's going to be in the background. From this, we just derive a reduced form. So parents invest. There is a mechanism of genetic transmission, which is here. And then parents invest, deciding how much they want to allocate between consumption and investment. The bottom line is the equation that you have on the evolution of the log of income. Now this is important. This I prefer to hear. This is the direct effect of income of the past generation. This is the effect of non-investment skills, which are the theta. Then there is this autoregressive structure on the skill. If you use this model, you compute the rho that doesn't have gamma in it. That's what the regression of the income that you get from this equation is on the previous income. Is the beta plus the autoregressive coefficient on the skill. There is no gamma in that equation. So we take this model and we introduce genes explicitly and see what happens to several quantities that are important. So the first equation is the log income as in the standard model. The heritable skill is a sum of a potentially large number of genes. The number of genes is going to be the crucial quantity here. We code the pair as 0, 1, or 2, depending on the lowercase a, capital A, and lowercase a on the capital A pair. We take complete assortative mating on income. Income, however, is noise, so there is not the perfect assortative mating is modulated by the noise on income, and then we do the steady state analysis of the joint distribution of the genes and income, and we see what predictions we have. So the main difference with the standard model is that now lambda and nu, which was the noise in the autoregressive structure in the standard model, become endogenous. become time varying and depend on the distribution, on the joint distribution that we are studying. So this puts a discipline on the process that we are studying.
Although, can I ask a question? Why switch? I'm just freaked out by the...
You are always freaked out.
I'm freaked out by the sun. And I'm just wondering...
The sun?
Yeah, why are you making this about genes? Why is this not about hereditable objects?
Why any hereditable object? Because I want to have a law that tells me how the G is evolving.
You've embedded in the law this notion that there's a monotonic relationship here, right? That you create...
No, that's just the... Okay, I'm not even assuming that 2 is larger is better than 1 is better than 0. That's just a relabeling. The only assumption I might be really making, but I'm not making it there, is that 1 is intermediate, is dominating in 0 or 2, so that you have a cusp. But
is the question about the empirical relevance? I'm sorry to interrupt.
No. Sorry.
What I mean by that is if he wants to make an argument about what would this say if the heritable object is genes, the distinct question is what if there are other objects?
I'm surprised by the assumption that you take a bunch of alleles and you treat them as having some scalar relation to the property of interest, and then you sum them up. Because that's clearly not what the story has been in the last 10, 15 years, right? The whole gene network nonlinear interaction stories raise for me the question of whether this classical model can really capture what we think happens when gene networks are interacting in these really complex nonlinear, non-monotone ways.
Okay, and I can take the most...
The question is whether you could use an additive approximation to these genetic effects. It works. I mean, that's what ag scientists do.
Well, I'm going to not take that bait yet. I promise
it works.
I think it's, in many cases where this has been studied quantitatively, the nonlinear component is a subdominant component of the additive variance. So this is a decent first approximation.
So I'm actually less, that's why I asked about heredity. Now, of course, to take the bait here. I'm less asking a question about hereditability and more asking a question about genetics. I mean, Aldo said genetics. That's one of the reasons I asked the question was I wanted to know if he was going to say, I don't really mean genes, I really mean hereditability.
No, I really mean, I would really like that. I would like this to be relevant, and I would like to test the implications of this in genome. Yes. So on these standards, I would like to test whether this is interesting or not. Okay. Mating rules, perfect asserted mating on Y. Once Y is given, remember that there is a noise. So you have to think there is going to be an invariant distribution on the product of genes and income that changes over time in 2 steps. First, you decide the pairing between the parents, the 2 parents, the mother and the father, depending on the income. Then you get the gene of the 2 children. Here is the 2 children, according to the standard rule. That is the discipline that this model is giving me. So the predictions I want, I have 3 parameters, and I have, so the beta, the effect on income, the gamma, the effect on the skill, and the variance of the income, and you get predictions on the mobility that we can estimate, and the inequality Gini, measured with Gini, which is the Great Gatsby curve, and you get the prediction that countries that are countries, the population that have higher inequality, they also have lower mobility. Second, which is the thing that I really care more about, is assertive mating will introduce a deviation from Hardy-Weinberg. I want to have a quantitative estimate how large the deviation is. And so now I will have, if I have a row that I want to match, I have a beta and a gamma that I can change. But by changing beta and gamma, I have a different effect on the deviation from Hardy-Weinberg. I can go and test on the genome data how large this deviation is. Is this an answer to your question? That's what I'm really trying to do. The conclusions that we find is there is a trade-off between gamma and beta. So policies that try to affect gamma and beta will have this unpleasant consequence that if you reduce inequality on one side, you can increase it on the other. The trade-off changes with the variance of the human capital or income process. And then finally, the third is that there is, which is a big difference from the standard model, I think there can be a high persistency at the same time that you have low variance. So the only way that you can have higher persistency in the standard model is to increase the beta, you're also increasing the variance. Because the lambda, the variance on the skill process is exogenous as independent, here is changing. Okay, so that's the predictions. We can make analytical and numerical simulation and test them in the data. That's what our plan is, 5 minutes. Okay, the logic is very simple and is already implicit in what Henry was presenting us. Look at the single gene and you see what is going on. Now you're looking for an invariant distribution on the product of 0, 1, 2 times y. Put first the variance to 0. Now you have a nice straight line. You have 3 populations that are completely separated. They mate within each other because the theta with the gamma is increasing the income according to 0, 1, and 2. So you have 3 separate populations which would have this income. But the one population goes down to 0. The frequency goes down to 0. So you have complete separation. That's an unrealistic benchmark, is what we really want to fight because it's contradicted by the evidence in the genomic data. But now we have to see how much you have to fight it off. So on the opposite case, when gamma is 0, you have, from the point of view of the process on theta, complete random mating, Hardy-Weinberg, and rho is equal to beta. In the intermediate case, which are more interesting, as you vary you change the variance on the process of income, you go from complete separation to mixing, and as the variance increases, the mixing increases, and deviation from Hardy-Weinberg decreases, but the effect on inequality and immobility decrease. So now we have this discipline, and we can find a good match with the data. This is the very simple intuition in the single gene. Now you put a larger number of genes, and you have the last piece of the puzzle. Because from the theory of assortative mating on phenotypes, you know that there is this very simple, very elegant. I mean, I think this was already in Fisher. If you look, the model I know are based on the very simple structure in which there is a fraction of the population is an assortative mating, and n is the number of genes, and f is, you can take it as a measure of deviation from Hardy-Weinberg, is the correlation in value among homologous genes, and the relation, and then you look at how much you deviate and what is the effect on the variance of the phenotype that you are studying. And this is the crucial thing. As n becomes large, the correlation becomes small, as long as you have at least a fraction of people that are doing the random mating. But the variance is increasing. Well, if n is large, this is 1, so this is v of 1 over r, so the variance is becoming very large. And what is going on is very clear. You have a very small effect of homozygosity added over a very large number of genes. You have a potentially large effect on the variance. But by maneuvering the beta, the gamma, and the variance of the shock, we can match also the data in the deviation from Hardy-Weinberg. In our model, something very similar happens. I don't have time to go to the detail, where the variance of the noise corresponds to R. So small variance is large R. Okay. How much do I have? 2 minutes? Okay. So that's the substance of what we do. I can show you what the magic of the number of genes as it increases. So you can simulate this. So this is going to be, I'm going to show you how the income distribution behaves as you change beta, as you change gamma, and then you change the variance. So I'll change the variance over time by changing the slides, and you can see beta and gamma. So this is as you go from up to down, beta increases. As you go from left to right, gamma increases. So this is Henry's separation. When the variance, this is very small variance. If you increase the variance, the separation tends to decrease. And then you can look at the implied rows, and you can check the trade-off.
So the same would be true if you increase the number of genes. That was all fixed at 5. If you go to 25, you get the same thing as the variance.
No, that's the main point. I'm getting to that if I manage to. So this is, we get the Great Gatsby. Unfortunately, we get a large deviation from our divine break. We can fix that, yes. That's what I'm going to do next. But I wanted to conclude this so you can estimate the rho and how it depends on the gamma. So you basically have this trade-off that I was saying that is a negative trade-off and becomes flatter as the variance increases. So the inequality, you can look at this as you go from this small beta and small gamma on the top left to large beta and large gamma on the bottom right, large inequality. And of course, there is also large immobility because people tend to stay in their class. Okay? How you can really simulate and see what the map between the beta, the gamma, and the variance is. You can look at the distribution of the gene, and you look at the bottom right, you get a very large deviation. So now the game is, now we have one more parameter, which is the number of genes, and by increasing that, can we get this, the bottom right, to be closer to the hard divine break? Maybe with a small deviation that then we can test. The answer is yes. So this is now a larger number of genes. It's only 20. Okay. The pattern now is no longer so striking binomial. As the variance increases, you get this. You see the pattern of inequality is less pronounced, but still you get the Great Gatsby qualitatively. So the relationship between the inequality and immobility, but you also have much smaller deviation. This is almost our divine break. Okay, thanks. 0 minutes. Thank you.
So Aldo, I wanted to reinforce the idea that there's something about a sort of mating and the Gatsby curve in the following sense. And that is, there's a number of models in economics, and slightly self-serving since I did some of them, that have this property that as cross-sectional inequality increases, that actually changes the incentives for sort of matching in some sense. And as a result, that translates the cross-sectional inequality into immobility. And so an example would be neighborhoods. And that is the incentives that families have to self-segregate can be increasing in the cross-sectional distribution of various characteristics. And that'll consequently create a map from the cross-section to the intergenerational. And I think in general that's a very fruitful way to proceed on thinking about these relationships. It will lead to interesting questions of identification as to whether, given the data we have available, we can differentiate the dimensions along which this decoupling, as it were, of different types in the population, is or is not salient. But I want to put on the table, I think that's a very important idea.
Yes. There's a sort of fundamental number that has to do with how much the next generation will resemble this one, which is to what fraction of the time is the father actually the father. And that is something people, there's sort of folk numbers about this. They will say things like 10% of the time the father is somebody other than what they actually are. Those folk numbers in the populations that have been looked at, which is like everybody in the United States and Europe pretty much, are wrong. Paternal uncertainty is low. So use a number like 1%.
Yeah,
I don't know.
it's very, very low.
Yeah, but the point is,
But
not
even
everybody.
in data, wait a minute, I thought that then when you look at data of blood donations, then it goes up substantially. Isn't
No.
that the story? No?
Here, I'll say a little more.
Okay.
But I told Greg Clark about this. I said, this helps your thesis because at least they really is the father. But here's what has been done. On some studies, for example, there were legitimate medical reasons to see who the father was because there were kids with leukemia in a big study in Germany, and there was a reasonable chance that they would need a bone marrow transplant. And in the course of doing that, you get enough genetic information to essentially perfectly know whether it's the father or not, unless it's his evil twin. Okay, and also one assumes that leukemia hits pretty randomly, so no special socioeconomic group was. At least not much difference anyhow. But in that group, about 1,000, the number of wrong matches with the father was about 1%. But people have also done this further because you can, if you look at surname analysis, but you say, like, we know that everybody with this last name is descended from this guy, at least originally. Over time, if there are false paternities, some of the people with that last name won't have that. They've also done this in some detail by other places would have detailed genealogical evidence, not just the surname. But you can see, this can tell you over the average amount of infidelity, also adoption, by the way, which would have the same effect. But by the way, which was rare in the past. Adoption was illegal in most of Europe until fairly recently. But which was a surprise to me, I hadn't realized that. But they have, the first version of this was Brian Sykes. He wanted to see how many people with Sykes, a moderately unusual last name in England, have essentially the same Y chromosome, which we know when originated about 700 or 800 years ago, and the answer was, I don't know, half or something. It boiled down to, I think, a false paternity rate of like 1.7% a generation. Those are the typical sorts of numbers, 1%, 1.5%.
Okay, it's
So
better than
that's-
I thought. I was afraid it was full.
I've seen this done in Boers, in South Africa, in recent one generation studies in Switzerland, Germany, several hundred-year studies in Brussels, in Belgium, in England, basically everywhere anybody's looked. But people have not looked everywhere, so you don't know in the next case for sure.
And where did this 10% number come from? I presume there's a study.
Well, the Decoupling study reported that, but I think it was that, I think people reported being the father when in fact they knew they weren't the biological father. So the Tecumseh goes way back. It's a study.
Well, there's also, some of it just came from nothing.
Yeah, folklore too.
Yeah, a lot of it's folklore. There's people who talk about much higher rates. As far as like 20%, 30%.
That's not right.
Yeah, they're just lying.
Ask Aldo a question.
Of course.
So Aldo, I'm sorry, I didn't completely follow your mathematics, but if I understood right, you said there's perfect assorted mating on income. Of course, there can't be. And so I think if you look at the assorted mating literature, or the marital resemblance literature, the two factors that mates, apart from age, that mates really resemble themselves on are educational attainment and political ideology. And both of those are extremely strong marital resemblance. Even something like IQ is not that high, and it's probably a consequence of education, which is
These are
probably a
your
function
data,
of-
you told me.
This is my data.
Yes.
Yeah, it's our data. Okay,
So this is the real uncertainty rating on the MTFR. So
So
this is
what
an
is the-
IQ traditional.
Yeah, well, traditionalism gets closer to political
Control.
ideology.
Yeah, that's, I put this as uncertainty rating on the
Yeah. It's actually more like 0.6 if you get a good measure of political ideology.
Okay.
But I think that's what but okay, the question is, what happens to your model if it isn't? I mean, the correlation got to be much lower than perfect.
So this is a first attempt. I'm willing to start throwing in this up, but then it becomes too easy, I think. Okay.
Okay.
Of course, the certainty mating is probably done in large part over theta, but then most of
From a mathematical point of view, you have a nonlinear difference equation.
on the equation I have is on the distribution on the product of gene and income. Yes, it's nonlinear.
Did you do a bifurcation analysis?
No.
Because it looks like a bifurcation what you are presenting. The splitting.
Okay, now I understand what you mean. Yes, if you look at the very simple case of the single gene, yes, it is, yes.
because you can do that.
There are economic models complementary that explicitly have these bifurcations.
Kind of an obvious comment, but probably if you want to make your model realistic, you've got to take much larger ends. I mean, reality is closer to n equals infinity than n equals y. And so then even if you did get segregating castes or whatever it is, the frequency differences on any individual locus would be quite small, but in aggregate there might be big phenotype differences.
Yeah, it will really help me. There are two major things. N has to be much larger and the weights have to decline exponentially, which are the things that we have learned since 2008. But it will help the case that you can get great Gatsby on one hand and very small deviation.
Even as n in the limit goes to infinity, the Great Gatsby function is preserved. It went by too fast for me to have an intuition on it.
Yes. Yes, because you are multiplying a very large for a very small.
Yeah. So that's the point.
Thank you.